So we're going to look now at a couple of different methods that we use to calculate delta H's of reactions. Now with both these methods, they're going to use delta H of reaction values that have already been determined experimentally. Okay, so let's start with Hess's law. So with Hess's law, it's going to center around the fact that delta H for any chemical reaction is going to be independent of the reaction pathway. So it doesn't matter how we get from our reactants to our products, what path it takes to do that. It's just a matter of what reactants we're starting with, what products we're ending up with. Okay, so remember, that's what a state function is. Okay, so enthalpy is going to be the state function. It's going to be independent of the pathway the reaction takes. All right, let's look at a simple example of this. So let me consider delta H of formation for the formation of CO2 gas. One thing to note here, you see that little knot, the little zero superscript next to the H there? That means we're under standard conditions. Standard conditions, thermochemistry-wise, is going to be 1 atmosphere and 25 degrees Celsius. It's different than the STP, the standard temperature and pressure we talk about when we're dealing with gases. So delta H deals with enthalpy, which is thermochemistry, so that little knot, standard conditions, means 1 atmosphere, 25 degrees Celsius here because we're dealing with the thermochemistry. Okay, so looking at this standard enthalpy of formation for the formation of CO2 gas, we could treat it as a one-step reaction. So if we form 1 mole of CO2 gas from its elemental forms in their standard state, so I take carbon solid plus O2 gas, goes to form CO2 gas. That reaction is a one-step reaction. Now, based on Hess's law, we could actually look at this and consider that delta H formation if we have a two-step reaction. So what if I took my carbon, reacted with O2, and first formed carbon monoxide? Then I took that carbon monoxide, reacted it with O2, and formed CO2 gas. I'm initially starting with carbon and oxygen, ending up with CO2 gas, so the overall equation hasn't changed, but it's now gone from a one-step process to a two-step process. But overall, either way, the delta H formation is going to be the same. It's independent of the path it took. We're only concerned with what reactants are we using, what products are we ending up with. Okay, so the overall delta H reaction for this process would be the delta H for the first reaction added to the delta H of the second reaction. One of the benefits of Hess's law is that we'll be able to take new reactions that may not be possible and determine a delta H value, even though we may not be able to actually measure that delta H value in the lab. We couldn't determine experimentally, but we could calculate a delta H for a reaction that may not be completely possible, or may be impossible to do in the lab setting. But we're going to use delta H's from known reactions, delta H's we've already know, okay, to do that. So Hess's law is going to allow us to do that. So let's look at an example of this. So let's say I want to calculate delta H for the following reaction. So 1 mole of hydrogen gas plus 1 mole of bromine gas goes to form 1 mole of HBr gas. Now, in practice, this reaction isn't going to be possible to be measured because we can't have a single monatomic hydrogen gas and single monatomic bromine gas because they're diatomic molecules. Okay? But even though we can't actually measure this in the lab, we can predict what the delta H is going to be. How are we going to do that? Well, let's pull up some equations where we know the delta H values from. And what we're going to do is we're going to use this information from these known reactions to help us predict what the new delta H is going to be. Now the best way to do this, start on the reactant side, start on the far left, work your way to the right. So what we're going to do is try to match up that equation and pull those moles and those compounds and elements from these equations, but we're going to have to rearrange some of these. So the best approach to take to this is going to be start from the left of our reaction we want, work our way across to the right, and all we're going to do is try to get each of those reactants, each of those products, and the appropriate number of moles of those from our given equations. So what do I mean by that? Well, if I start with H and have a single H gas, which of these three equations contains H gas? Well, the first one does. So let's look at the first one. So if I take that first equation, I've got H gas in the product side, but in my final equation, I've got H gas in the reactant side. So how do I deal with that? Well, what I can do is reverse the equation. So now I have 2H gas going to form 1H2 gas, but when I do that, when I flip the equation around, I'm going to have to change the sign to the delta H of the reaction for that. I've gone from a positive 436.4 kilojoules to a negative 436.4 kilojoules. Now the other problem I have though is I have one H in my final reaction, I have two H's in my current reaction. Even though they're both on the reactant side now, well, how do I deal with that? Well, to deal with that, I need to basically multiply that equation by 1/2. So I end up with a single H on the reactant side and 1/2 H2 gas on the product side. Because I multiplied by 1/2, basically I divided everything by 2, I have to divide my delta H by 2. So for that equation now, I end up with a negative 218.2 kilojoules. Now, just to keep track of things, I know I've used that first equation. I'm not going to use it again, so I'm just going to put a line through it so I know not to use it again. Okay, and then I need to move on to the next part of the equation. Well, in this case, it's going to be my other reactant, which is Br gas. So where is Br in the remaining two equations? What's in equation number 2? So if I take that second reaction, equation number 2, so what do I have to do with my second reaction here? Well, first I have to flip it to get my Br on the reactant side. Now I've got two Brs on my reactant side. I need to then multiply by 1/2 to get a single Br gas. And remember, whatever I'm doing to the equation, I'm doing to my delta H value. Okay, so let's say I had to multiply by 2 instead of divide by 2. Well, then I would multiply my delta H value by 2. Okay, so when I flip the equation, I take the negative value, and then whatever I'm doing to the reaction in terms of multiplication division, I do to my delta H. All right, then I go back to my list. I've now used the second equation, so I'll cross that off as well. And now I'll go back to my reaction I'm trying to find delta H for. What's left? Well, I have HBr on the product side. Well, which of these equations has HBr in it? Well, the third one does. So let's look at that third one. It's already in the product side, so I don't need to flip the equation. I'm good there. But I do have two of them. So what do I need to do? Well, I need to multiply that equation by 1/2, which means I take my delta H and divide it by 2, or multiply it by 1/2. Okay, put a line through my third equation. I've used them all. And then what I'm going to do is I'm going to look at all of those new equations that I came up with, those rearrangements of those original three equations, and put all three of them together. And so I put all my reactants on one side, all my products on the other side. And then I can cancel similar things out. So you can see I've got 1/2 H2 gas on the reactant side, I've got 1/2 H2 gas on the product side. Those could cancel. I have 1/2 Br2 gas on the reactant side, 1/2 Br2 gas on the product side. Those can cancel out. So when I do that, I end up with my overall equation of H plus Br goes to form HBr gas, which is what I want my end equation to be. Okay, this is a quick way to check to make sure I've done my rearrangements properly. So once I've got my overall end equation that I want, after adding up all my rearranged chemical reactions, then all I need to do is take all those new delta H's I came up with, add them together, I get my delta H for my overall reaction. So my overall reaction has one hydrogen plus one bromine goes to form one HBr, and I have a delta H for that reaction. If I go from the three separate equations though, I could have one hydrogen going to form 1/2 H2 gas, one Br going to form 1/2 Br2 gas, and then 1/2 H2 gas plus 1/2 Br2 gas goes to form one HBr gas. Overall, it doesn't matter whether I do it in 3 steps or that one overall step. Either way, my delta H of reaction is going to be the same. Right? That's what Hess's law deals with. Okay, let's go through another example of this. So I want to calculate delta H for this reaction. I'm given the following information. Now this looks a little bit more complicated, but follow those rules I gave you. So we're going to start from the left-hand side and work our way to the right. So left-hand side, I have CLF gas. Which equation do I have CLF gas in? Whether on the reactant or product side, either way. Well, I have the CLF gas in the first equation, and it's on my reactant side. Taking that first equation, I don't need to flip it around because it's already in the reactant side, but I do need to divide by 1/2. Okay, so I get my new delta H for that. Notice I didn't change the sign because I didn't flip the equation around. So I go back to my list, Put a line through the first equation because I just used it. What's next? The F2 gas. Well, where's F2 at? Well, it's actually in the third equation there. So starting with that third equation, F2 gas is in the reactant side already. I want it in the reactant side, so I don't need to change the sign of the delta H. But I do have two of them, so I need to divide by 1/2. Go back to my list. I need to put a line through my third equation. And lastly, I need my ClF3 gas. I need that in my product side. Well, where's the ClF3 gas at? It's in the second reaction there. It's in the reactant side in this equation, so I need to flip it first, and remember I changed the sign of the delta H. Now I've got two ClF3s. I only want one, so then I also need to divide everything in half. Okay, so I've used all my equations. I've got my new equations now. So rewrite everything, add up all the reactants, add up all the products. Whatever is equal on both sides cancels out, and when I do that with this, I end up with my ClF plus F2 gas goes to form ClF3. Okay, which means I can add up these three new reactions, add up their delta H's, and get my delta H reaction that I'm looking for. So that's dealing with enthalpies of reaction and Hess's law. Hess's law deals with the fact that it doesn't matter how we get from reactants to products. All we're concerned about is what reactions are we starting with, what products are we ending up with. The path in between doesn't matter. It's going to be the same change in delta H regardless of the path we take. Okay, which allows us to rearrange these equations and use Hess's law. Now, another method commonly used to determine delta H of reactions is going to be using something called standard enthalpies of formation. So with standard enthalpies of formation, that's going to be the heat change due to 1 mole of a compound being formed from substances in their standard states at 1 atmosphere and 25 degrees Celsius. So for a chemical reaction then, we can use those standard enthalpies of formation and calculate an overall delta H reaction using those enthalpies of formation. So delta H reaction is just going to be sum of the products minus sum of the reactant. Products being our final state, reactants being our initial state. So we're still doing that final minus initial, it's just we're dealing with delta H's now. All right, so let's look at an example of this. So we want to calculate delta H for the following reaction. Now, in order to calculate delta H reaction, we need to actually get these standard enthalpies of formation. Those are available in a table, so you can find them in a standard enthalpies of formation table. When we look each one up, we have to make sure to note the state that they're in. So the C2H5OH is in liquid form, the O2 is in gas form, the CO2 is in gas form, the H2O is in gas form. Because when we look up those values, they are going to be dependent upon what phase those materials are in. Okay, so when you look these values up, make sure to note those. All right, so when I look these values up, I get the following delta H of formations for each of these different compounds. All right, and I'm going to use these delta H formations to help me calculate that chemical reaction. And don't forget, we're going to do sum of the products minus sum of the reactants. Now you may notice there's an N and an M in this equation. Those are going to relate to the moles in the balanced equation. All right, but we're going to walk you through this calculation. So I've got my standard enthalpies of formation. I know the equation I need to use. So I'm going to plug these values in now. Remember, I'm doing products minus reactants. So I look at the CO2, which is the first product. It's a negative 393.5 kilojoules per mole, which means for every mole of CO2 produced, I'm going to get a negative 393.5 kilojoules. So I need to take the 2 moles from my balanced equation times that negative 393.5 kilojoules per mole. All right. Then I'm going to add that to the 3 moles of water. That's my sum of my products. And then I'm going to subtract from that the sum of my reactants. I've got the 1 mole of my C2H5OH, and then I've got the 3 moles of the oxygen gas. One thing to note with standard enthalpies of formation, anything that's in its elemental standard state is going to have an enthalpy of formation of 0. So since O2 gas, oxygen exists as O2 gas in its standard state, it has no enthalpy of formation associated with it. Okay, so we plug these values in, run the calculation, and we end up getting a delta H of reaction for this of a negative 1.235 times 10 to the third kilojoules. Okay, so there's a couple of different ways we talked about. We talked about using Hess's law to determine this delta H reaction. We talked about using standard enthalpies of formation to calculate a delta H reaction. Either one can work depending upon what information you're provided with. All right, but that's going to be it for these calculations using Hess's law and standard enthalpies of formation.